Hello everyone, I'm Angelica and I'm going to present our work named Discrete Element Method and Finite Element Method Combination applied in the simulation of zinc-based code. This presentation is organized as follows: Introduction, the L-Dyna, methodology, results, and conclusions. So, the hot dip galvanizing is a widely used technique to protect structural steel due to its inherent capacity to long last without requiring any maintenance. The technique consists in the formation of a protective layer of zinc on the surface of the steel. The benefits of this technique are create a barrier between the steel and the environment, and the cathodic protection offered by zinc corroding itself instead of the steel due to the different electromechanical potential of these two materials. In the last years, there has been an increasing research on zinc coatings in order to optimize the phase thickness and the mechanical and physical performance. It is proposed an approach for numerical modeling of pure zinc-based coatings hot-rolled hyper-sandling steel. So our goal is to use a hybrid model with discrete element and finite element in a unique model to simulate the damage evolution. Some experimental bending tests available in the literature were used to compare fracture partners. So, the lattice discrete element method consists of a set of masses joined by bar elements characterized by a regular cubic arrangement. The bars are characterized by a linear constitutive law, which always to take into account the reversible effect of crack nucleation and propagation. It is a law that considers the residual deformation when unloaded. In the lattice discrete element method, a random field is introduced for the fracture energy, and as consequence, the randomness is indirectly assigned to a critical strain using this equation. The critical strain is the strain that the crack starts. So, the fracture energy is modeled by a Weibull probability distribution. The LD was implemented in the ANSYS LSDyne environment, thus creating a hybrid model named the LD-Dyna. The LD-Dyna model always uses both elements, discrete elements and finite elements in a unique model. More precisely, the region where the fracture is expected to occur is modeled by means of discrete elements, and the rest of the model is simulated by finite elements. So, the experimental tests were performed on a hot dip galvanized specimens under constant bending moment. The longitudinal sections of the specimen were experimentally observed by a light optical microscope lume to measure both the phase thickness before test and the level of damage after test. The specimens were manufactured from the hot-rolled hyper-sandling steel plates. Here we have the specimen geometrical configuration. Here we have the geometry of the model simulated, and the phases zeta, the steel, and the interfaces are simulated in finite elements, and the phases zeta and delta are simulated in discrete elements because in this region is expected that the fracture occurs. So, here we have the boundary conditions, and the table 1 shows the thickness of each phase formed by a dip time equal to 50 seconds. The table 2 shows the mold discretization and the materials. Here we present the results in terms of damage evolution when we apply the prescribed displacement equal of 5×10⁻⁻6 meters. So the percentage represents the maximum displacement applied. So when we have 30–50% of the displacement applied, the damage started in the both phases zeta and delta, and when we have the 50–75% of the displacement applied, appears the first crack. In the next stage, in the end of the simulation, occurs the appearance of a second crack. Here we compare the experimental results obtained by Loom and the numerical results in terms of crack distance. We can observe that the distance between the cracks are similar, and we can observe in the simulation that the green region represent the regions that the bar not damaged. The orange region represent the region where the bars damage, and the red region represent the bars that broken. So we can observe that here in the middle of these two cracks, we have a region that the bars damage. So it's probable that when we apply a bigger displacement, we have a third crack in this region. So the numerical model developed has been shown to be able to capture similar qualitative information about the damage process in zinc-based coatings. The possibility of carrying out the union between discrete elements and finite elements will allow in future works a quantitative analysis of the experimental results. And the next step of this work is to evaluate the damage in ordered samples with different dipping times and consequently different phase thickness, which, as in Dyna, it will also possible to compare the results in terms of applied moment versus bending angle with the data obtained experimentally. So thank you, and please for any question contact me by email.